Hi, and welcome to Lakehouse with Delta Lake Deep Dive. My name is Kate Sullivan, and I'm a technical curriculum developer at Databricks. I'll be leading you through the activities for this session in the lecture, and we will also have some teaching assistants available to answer any questions that you have as you go through the material. So if you have questions, please type them into the Meeting Play platform, and we can answer them for you. Okay. So let's first just go over the course objectives so that we're all aware of where you're going to end up by the time you finish this course. By the end of this course, you should be able to define some core characteristics of the Lakehouse architecture. Also, you should be able to explain how Delta Lake supports the Lakehouse architecture. We're going to go through an example of how to build an end-to-end batch and streaming online analytical processing data pipeline using Delta Lake. So you should be able to broadly explain sort of how to do that. Throughout that process, we're going to follow some specified design patterns to make data available for consumption by downstream stakeholders. And you should be able to explain Databricks' recommended best practices in engineering a single source of truth using the Delta design pattern. Okay, great. And also just to let you know how the day is going to break down, please take a look at this agenda. We're going to start with a 20-minute introduction to the Lakehouse and Delta Lake. And then we're going to get into the weeds a bit by going into a Delta Lake deep dive and sort of seeing some of the things that make Delta Lake work. And we're going to take a little break so you can step up away from your computer and stretch your legs. And when you come back, we're going to start with the demo where we'll be first ingesting data, showing you how to do that using Delta. And then we're going to start building your single source of truth. And then after we finish that, we'll have another little break so you can, again, get up, have a little stretch. And then when you come back, we're going to talk about maintaining your single source of truth and actually delivering those end user tables that we just talked about. And then we'll come back to sort of a lecture setting and go over a quick summary of what we learned. All right, so with that, I think we're ready to get started. And we're going to do that by introducing this idea of the Lakehouse, in case you're not already familiar with that. The Lakehouse is a fairly recent innovation in data architecture that can help you simplify your data workloads, ease collaboration for your data teams, and maintain the kind of flexibility and openness that allows your company to stay agile as you scale. In order to understand how the Lakehouse works, it can be helpful to consider some of our other architectural patterns that came before it. So we can see we have a sort of a data warehouse and a data lake feeding into this idea of the Lakehouse. So let's take a look at each of those individually. So we'll start with data warehouses because just historically, they were sort of first on the scene to help us start working with data in the way that we want to and answering some of our business intelligence questions. So we want data-driven businesses. Creating these data-driven business intelligence applications is a good place to start. So we define questions, basically, and we need to know answers. And so we construct the engineering pathways to serve this data all up into our team of analysts. And these are usually really well-defined questions like how are sales, or what does my supply chain look like? And all really important things to understand when you're trying to grow your successful business. But when you want to ask different questions, specifically those around machine learning or data science, which is the bulk of our more recent use cases, you'll start running into some problems because there's very limited support for machine learning. You're dealing only with structured data here, and a lot of the data that you want to work with is going to be unstructured. Also, you're working with proprietary systems that can make it really easy to get your data in. but it's really difficult to get your data back out if you ever want to move it into a new system. So if you have an only SQL interface, that restricts you to the things that you can do just within that system. Also, they can't really support streaming data, so you can't act on data as it comes in. And by the time the data actually reaches their end users, it may be stale or just incorrect. So how do we address those issues? Well, again, historically speaking, data lakes entered the scene about a decade ago, and a lot of that, and they answered a lot of the challenges that were being serviced by data warehouses. So they can support your data in any format, first of all, right? So we can keep any data in there. There's basically no limit to how much data you can collect, and it can be any kind you want. And it can be all in open formats in this big ecosystem to support it. You have all this data, and you can operate it with any form, so you can do all the ML, all the machine learning that you'd like to. But a data lake on its own can really quickly become a mess. It can get polluted with bad data and or old data. It can have a really slow query performance because the data isn't well organized, so it's really difficult to retrieve. And then once you do retrieve some bit of data, it's hard to tell whether or not that is the most reliable, most up-to-date bit of information that you need. So we have these two systems, and neither of them sufficiently meets all of the enterprise needs. So this is a pain that a lot of people are feeling today because most enterprises struggle with data. We end up cobbling together a system that only sort of works, right? We build a bunch of data silos depending on what you're actually trying to do. So we're building actually 4 different stacks here, right? We've got our data warehousing stack that serves our analytics and BI. We've got our data engineering stack that focuses just on taking in that structured data and sort of preparing it for other use cases. We've got our streaming workloads that have to operate on a whole different system. And then we've got this work that will be siphoned off to go to data science and machine learning. And the way that people are using these are all really different technologies, and they don't really work well together. The architectural complexity here is actually further hampered by the overall ecosystem. So we've got tons of different tools in each of these stacks, and they don't necessarily work well together. Remember that when we're dealing with data, we're usually dealing with one whole use case at a time, right? We're not dealing with a data warehousing problem or a data engineering problem. We're dealing with all of it at once. And so that means that we need to move this data across these systems using these tools that don't really cooperate. And all of this complexity can really slow down development. Because the systems are siloed, the teams become siloed too. So that thing that we said where we're trying to tackle this whole data problem is broken down into all these different pieces, and it can be really hard to communicate with each other about what you need from the data and what the data can support and how quickly you can get there. When communication slows down, that certainly hinders innovation and speed. And then if you've got all this data floating into these different places, we end up with different teams actually using different versions of the truth. So the result is just multiple copies of data and no consistent security or governance model, closed systems, and disconnected, less productive data teams. So we look at all this and we think there's got to be a better way. And that's where the Lakehouse comes in. Lakehouses are enabled by a new system design, implementing similar data structures and data management features to those in a data warehouse, directly on the kind of low-cost storage used for data lakes. They are what you would get if you had to redesign data warehouses in the modern world, now that cheap and highly reliable storage in the form of object stores are available. So this is the big idea, and it's simple and intuitive. We have two systems that aren't quite working right, so we want to take the best parts of both. I guess the trick here then is how can we actually pull this off? How can we actually deliver the data management capabilities of a warehouse when you're actually working on a data lake? And the answer is that it's Delta Lake that provides that critical layer of modern lakehouse architecture, bringing structure and reliability in support of any downstream use cases. We can better understand how that's actually working if we take a closer look at how Delta Lake enables the modern lakehouse. And we should do that by stepping back and examining some of those problems that we gave kind of in brief around dealing with data lakes. There are really 10 complaints that we've heard a lot, and we'll go over each of those. The first one is something that is as simple as just appending new data using Spark into the data lake, while at the same time trying to read it consistently. This has caused a ton of issues. Obviously, users want the changes in their data to appear all at once, but this is really hard to achieve because making multiple files appear all at once, or even a single file appear in its full form, wasn't really supported out of the box with data lakes. Second, modifying data is hard, especially with the regulations that are in different jurisdictions. It's required that if a user doesn't want their data to be stored, then you have to be able to delete it. And if you have it in a data lake, it becomes actually a challenge to just delete a single record. It can be very costly to do. Some would come up with manual techniques for it, but it would rewrite entire petabytes on the data lake once a week to sort of clean it of the things that needed to be removed, which is expensive and time and money. Third, we've got the issue of jobs failing midway through. So if you have a streaming job and it fails, the cluster goes down, and then months later when you're trying to access the data, it turns out only half the data is there. It can be really hard to tell even if you're working with a corrupt record. Fourth, organizations have been promised that they can mix real-time operations and do things like that on these systems. But it turns out that mixing streaming and batch ingestion can lead to inconsistency. This is a variation of that first problem that we talked about with appends, but mixing in real-time operations and batch leads to inconsistencies where you're reading partial results. Fifth, many regulated organizations need to keep all of the versions of their data, and they need to reproduce any data set they ever had for auditing and governance reasons. So it turns out that is also very hard to do. So what they would do, again, is manually make lots of copies and snapshots of the data. This can be time intensive, but also really costly. The sixth challenge is that it can be really hard to handle large metadata. If you have petabytes of data in the data lake, then the metadata itself becomes gigabytes, and most of the catalogs out there can't support those sizes. 7, we hear about the too many files problem. Again, since data lakes are file-based and you end up with maybe millions of tiny files, or maybe you have 2 really gigantic files, in either case, you can impact performance by just having unknown difficult to deal with file sizes, unpredictable file sizes. And 8, on that same note, it's generally just hard to get great performance. You have to do a lot of manual techniques like partitioning, and these techniques are, of course, error prone. 9, data lakes make it hard to lock down access to your data. Again, making it hard to know if we're even complying with those privacy laws. And last but not least, all these issues lead up to data quality issues. It's really hard to ensure that your data is correct and clean. It's especially hard in the big data world because you can't skim through your data manually to see if it looks okay. But Delta Lake was actually designed to handle all of these challenges associated with data lakes. It's an open source project that's in the Linux Foundation, but it did start at Databricks. And it was meant to add reliability, performance, and governance and quality to existing data lakes, right? It takes the reliable ACID transactions that we expect from warehouses, the performance that we expect from warehouses, governance and quality, and it lets you have all of that on your data lake. You get to keep your data instead, though, in open formats, so you don't have to move your data anywhere, and your data always stays accessible to you. And instead of the complicated web of systems that we looked at earlier, it allows you to simplify all of that with a curated data lake approach. As we move through each of these different stages, the bronze, silver, and gold, your data is all staying in a pipeline, and it's getting progressively cleaner as it gets cleaner and more organized as it moves through to your end users. So the first 5 deal with reliability and are actually addressed by adding in ACID transactions. ACID transactions are the way we make every operation on your data lake transactional. That means that every operation either fully succeeds or we abort it and we clean up any residue so that you can't notice it and you can retry it later. Delta Lake does this by keeping a transaction log of every operation. That's the image that's shown here of all of these numbered JSON files. Right, we're keeping a transaction log, and we make sure that everything in that table is consistent with that transaction log. We'll talk a lot more about that later on in this session. This also allows you to mix real-time and batch ingestion because real-time and batch operations are now consistent with this log, and Delta enables you to do time travel. So since we have all these deltas, all these differences in the transaction log, we can actually go back in time and look at any version of the data. Okay, so now we can do appends because the transaction log makes sure that they're consistent. And we can also modify existing data because the transaction is allowing you to do small, fine-grained updates. Things failing halfway through just won't happen. We also know that real-time operations will be consistent and the historical data versions will be there as well. And now, how does Delta handle large metadata? Well, it just uses Spark under the hood, really. So if we use Spark, Spark was built for managing big data. So we're using Spark for actually managing the metadata, which enables us to scale infinitely. The data and its metadata always coexist. To help us address some of the performance issues, Delta Lake has indexing. We have partitioning, but we also have things like Bloom filters and data skipping, which are various statistical techniques that let us, when we get a query, look at the data and actually avoid reading big portions of the data altogether, and therefore we get massive speedups. We have Z-ordering, which lets lay out the data in a way that you can actually have multiple columns that are all optimized equally, and therefore a query, if you had a year, a month, or a day that goes through the day, month, or all three, they can get similar performance. And then finally, we have auto-optimize, which periodically relays out the data in the background so that it's optimized for later usage. For instance, if you've got a lot of tiny files, auto-optimize will compact them and make them consolidate them into bigger files. We'll go over that in more detail a little bit later. Before we had poor security in when we're using Delta, we can actually use table ACLs to programmatically set access to data objects and dynamically mask views based on users' credentials. This also makes it easy to monitor governance and know where your data is, where it's coming from, and how you want it to flow through your system. And finally, how do we make sure that we can deal with data quality issues? Well, here, Delta comes with schema validation. And that means that every Delta table must adhere strictly to the schema. So if you have a star schema or some other schema, we'll make sure that it always satisfies that schema. And if it doesn't, we'll move that data into quarantine where you can go back and look at it later and fix it. We'll take a look at how schema validation works later on in the demo. All right, so in the next section, we're going to talk about some elements of Delta Lake, and that is specifically the Delta design pattern and also the Delta transactional layer. So we briefly talked about this before. The Delta Lake design pattern keeps all of your data in this single system and consists of landing data successively in cleaner Delta Lake tables from your raw data, which is in a bronze level table, to your clean silver level table, to your aggregate gold level table. This is also referred to as a multi-hop architecture. This pattern is a vast improvement on the traditional Lambda architecture. At each stage, we're enriching our data through a unified pipeline that allows us to combine batch and streaming workflows through a shared file store with ACID-compliant transactions. Each stage can be configured as a batch or streaming job, and atomic transactions ensure that they succeed or fail completely. The end outputs are actionable insights, dashboards, and reports of business metrics. By considering our business logic at all steps of this ETL pipeline, we can ensure that storage and compute costs are optimized by reducing unnecessary duplication of data and limiting ad hoc querying against full historical data. So let's visit each of these tables individually. Bronze tables are the raw data that are ingested from various sources, like JSON files or RDBMS data. Could be IoT data that you have streaming in. And we can keep all of the data in inexpensive commodity object storage, such as bronze tables. The data in a bronze table often has a long retention, like a matter of years, and can be saved as is, avoiding error-prone parsing at this stage. The silver tables hold your filtered, clean, augmented data. They provide a more refined view of the data, and we can join fields from various bronze tables to enrich streaming records, or we can update account statuses based on recent activities. All these events are cleaned and normalized, and sometimes joined with dimensional information. So the silver tables are called the sort of single source of truth for the company, right? This is data that's reliable, but it's not necessarily, in our flattened or aggregated gold level tables, which we're going to talk about right now. Our gold level tables provide our business level aggregates, and they're often used for reporting and dashboarding. This would include aggregations such as like daily active website users, or weekly sales per store, or gross revenue by quarter or by department. These are usually related to one particular business objective. So you'll have your silver tables, and they'll feed many different gold tables, and the gold tables will feed into a variety of like streaming analytics and reporting use cases. All right. So the Delta transactional layer is really what transforms a data lake into a Delta lake. It runs on top of the cloud storage, and it holds all of your data. So if keeping all of your data and files in object storage is the central design pattern that defines a data lake, you get to still do that, but then just on top of it, we have this structured transactional layer that tracks and indexes those files, providing data management and governance capabilities on your data lake. So then we can use one platform for all of our data use cases. We've got streaming, BI, data science, and ML. On top of that, we're applying a high-performance query engine to offer improved price and performance for all of your workloads. And it's for all these reasons that we can say that Databricks offers a complete Lakehouse platform. It operates in the cloud and across all the clouds, so it's at once multi-cloud and tightly integrated with all of the different cloud capabilities for a given provider. Your data gets to remain in an open data lake. Databricks with Delta Lake delivers the management and governance to ensure security, reliability, and performance. It also supports all workloads on one platform, from data engineering, BI, data science, and real-time applications. Keeping all of this work on one platform simplifies the work of the data team and allows for easy collaboration. So, just to review some benefits of the Lakehouse, we've got this separation of compute and storage. You can keep, your storage is basically infinite, right? We're just keeping things in the data lake, and we can keep compute separate than that, and it makes it easier to allocate resources elastically. Which means a data lakehouse is the least expensive options for building a single source of truth, because organizations pay for compute only when needed. Also, it's allowing you to leverage the best aspects of a data warehouse without actually having to use one, right? We still get to keep all of our data in a data lake, but as you move your data through the system, it's getting progressively more refined and sorted into its appropriate use cases. So that your end users, your sort of analyst team, they can query data, they get super fast performance, and you're still getting all of your business questions answered with reliable, up-to-date data. There's extremely low data gravity here. The organization's cloud object store keeps data in whatever format you choose, so your data always is going to belong to you. And you can actually move it from here to any other location or format. The Lakehouse provides high data throughput, and that refers to this architecture's ability to handle a much higher volume of data per unit of time. And there are no limits on data structure. Using a data lake as the single source of truth means that there are no limits on the kinds of data that can be ingested. And finally, remember that you can mix batch and streaming workloads. Building a system with Apache Spark means that the system benefits from the structured streaming capabilities of Apache Spark. So that's a brief introduction to the Lakehouse and to Delta Lake, which really forms the foundation of our Lakehouse. Now, let's get into some of the details that make Delta Lake work. In this section, we'll focus on the following core components important for understanding Delta Lake. And those are Delta tables. We should understand how Delta tables are stored. And also the commit service, which deals with the transaction log. We should understand how changes in the Delta tables are processed. So a Delta table is a collection of data kept using Delta Lake technology and consists of three main things. We've got our Delta files, right? And Delta Lake uses parquet files that are stored in object storage. If you're not familiar with it, Apache Parquet is an open source file format that is designed for efficient and performant flat columnar storage of data. Compared to like row-based files like CSV or TSV files, it's much more efficient than that. So these Delta Lake files are actually Parquet files, but then they are also kept with a transaction log, and that's the Delta bit. The transaction log kept with the Delta files stays right in object storage with them. And then we also have tables that are registered to a table registered to the metastore. So technically, you can have your Delta files in place and your transaction log, and you don't necessarily need a table registered in the metastore. So this step is technically optional. But if you want to be able to write SQL queries against your Delta table, it's necessary. And metastore references include the location of Delta files and object storage, in addition to the schema and properties of the table. Once registered, your users can write Spark SQL queries against a table registered in the metastore. In other words, end users will write simple queries against a Delta table as if they were interacting with a standard SQL database. So let's focus in a little bit on that transaction log, because it's really important to how Delta works. The transaction log makes it possible for multiple readers and writers on a given Delta table to work at the same time. It serves as a central repository that tracks all the changes that users make to a table. The metadata can be stored and accessed easily as part of the transaction log. As we can see here, down at the bottom of the screen, we've got this scalable metadata that is just easily accessible by reading the parquet file. When a user reads a Delta Lake table for the first time or runs a new query on an open table that has been modified since the last time it was read, Spark checks that transaction log to see what new transactions have posted to the table, and then it updates that end user's table with those new changes. This ensures that a user's version of the table is always synchronized with the master record as of the most recent query, and that users cannot make divergent or conflicting changes to a table. The transaction log is broken down into a series of atomic commits, where each commit is recorded as a JSON file. And then Delta Lake retains those atomic commits to ensure that in the event we needed to audit the table or use time travel to see what our table looked like at any given point in time, we could do so accurately. We'll talk during the demonstration about how you can use time travel, but effectively it's a way of looking at different versions of your table over time. So once we've made 10 different commits to that transaction log, Delta Lake saves a checkpoint file in parquet format in the same Delta log subdirectory that is included with the rest of the files. And Delta Lake automatically generates checkpoint files for every 10 commits. So, for example, in this we can see that we're reading a parquet file, and it is our first checkpoint.parquet. And then within that, we can see some details about the table metadata. Those checkpoint files save the entire state of a table at a point in time, and in native Parquet format, so it's quick and easy for Spark to read. In other words, they offer the Spark reader sort of a shortcut to fully reproducing a table state that allows Spark to avoid reprocessing what could be thousands of tiny, inefficient JSON files. So the transaction log provides that key ingredient for adding reliability to our data lake. To better understand the transaction log, we're going to dig a little bit deeper into the commit service. The commit service is what controls how the transaction log is written. So, as I said, all changes in a Delta table are stored as those atomic units, those commits. And they contain the schema and metadata, like some table statistics and things like that. So each of these commits is just tracking these small individual changes. And then they're going to get all packaged up together to create a checkpoint file that logs the table state exactly as it is at a point in time. So all this is recorded as a set of serialized transactions. And it's important to remember that one person can be applying changes to a table at any given time. So recording transaction in series is actually really important. We need to agree on the order of the changes even when there are multiple writes and writers. So let's look at an example here where we've got this first commit. We've got two users. So the first commit writes to a Delta table. That's represented there. User 2 is writing to that second version. And then what happens when they are both trying to write to that that third version that's listed there. Well, let's see how Delta would handle it. Delta uses optimistic concurrency control to deal with concurrent transactions. That means it assumes that transactions made to a table by different users can complete without conflict, right? That's the optimistic bit. So given that we're dealing with data at scale, which could be really, really big, like petabytes of data, there is actually a really high likelihood that two users won't be working on exactly the same part of the data at exactly the same time. So this optimistic concurrency model allows users to complete non-conflicting transactions simultaneously. And that means that the work can go really quickly. Works well for distributed systems. For example, let's imagine that you and I are both working on a jigsaw puzzle together. As long as we're working on different parts of it, like if you were working on the edges and I'm working on my own on a middle part, there's no reason that we can't both work on our parts at the same time, and then we can finish the puzzle twice as fast. It's only if we were to need the same piece at the same time that there's a conflict. Right? So the optimistic concurrency control is making the assumption that we're sticking to our different parts of the puzzle. In contrast, pessimistic concurrency control, which is in place in some other databases, it assumes that there will often be conflicts. Like if some part of the data is getting updated, that means that it shuts the whole rest of the access to data down, and it locks it up until the update is complete and then access is restored. So in a distributed system, that model can be super problematic. So in order to offer ACID transactions, Delta Lake has a protocol for figuring out how commits should be ordered and determining what to do in the event that two or more commits are made at the same time. Delta Lake handles these cases by implementing a rule of mutual exclusion and then attempting to solve any conflicts optimistically. This protocol allows Delta Lake to deliver on the ACID principle of isolation, which ensures that the resulting state of the table after multiple concurrent writes is the same as if those writes had occurred serially in isolation from one another. So let's take a look at this example to better understand how this all works. Imagine that two users are reading from the same table, and then each go about attempting to add some data to it. Delta Lake is going to handle these cases by implementing a rule of mutual exclusion and then attempting to solve any conflict optimistically. So in this example, those two users are reading from the same table. They both get that 0 JSON version of the table. They both append some data, right? But there's a conflict, right? Because they can't both commit to that second version of the table, that second JSON commit. Delta Lake handles this with mutual exclusion. So user 1 commit is accepted and user 2 is rejected. However, instead of throwing an error, it actually checks for those new commits and then processes user 2's commit on that newly updated table. So just to summarize, commit service, again, controls how the transaction log gets written in Delta Lake. And one core component of Delta Lake is the transaction log. It contains a series of atomic commits, as JSON files, which are grouped together as parquet checkpoints. Optimistic concurrency allows for multiple concurrent reads and writes while still maintaining a strict and serialized record of ACID transactions. Great. Okay, well, we've worked a lot to define sort of what the Lakehouse is and what Delta Lake is and exactly how Delta Lake works to guarantee those ACID transactions that bring reliability to your data lake. Now, let's go ahead and look at it in practice. I'm going to log into Databricks Workspace and start up a cluster and get ready to run that, to build that online analytical processing pipeline that we were talking about earlier. Go ahead and take a break, and then when you come back, we'll get started on the demo. In this section, I'm going to be working through a demonstration. This is not intended to be a hands-on course, but we have included the DBC that includes all of the notebooks that I'll be working through. If you do want to follow along using Databricks Community Edition, we have created a special link for you to use so that you have priority access to that platform. You can open this link by going to the Workspaces tab for this session and clicking on the Launch Workspace button. But for the most part, you can just follow along with me as I work through the video, and you can use the DBC at some point later. We'll start with 00 ingest raw. Just so you know how all this is going to work, I'm going to go through each of these notebooks step by step. We're going to talk about what's going on in our data pipeline, how we're going through each of these commands, and sometimes you're going to come to a place that says something like fill this in. It'll be marked with that to-do tag. You can fill in those pieces as we go through the course. So you have a couple of options. You can either work alongside and have two windows open at once and work right alongside me, or you can try it on your own, and if you ever get stuck, there is a solutions folder that is included with this DBC. You can see that they're all broken up into the same notebooks, just the solutions folder, instead of having the to-do tag, will have an answer tag, and that contains the correct answers for each of the activities that you're asked to complete. Okay, so we're going to first start off by making sure that we've got a running cluster. As you can see, I'm all set with mine. Okay, now in this notebook, we're going to be ingesting data from a remote source into our source directory raw. We'll talk in more detail once we get to see the data. Okay, so for now you should know that we are working with a streaming platform to ingest the data that's collected from these fitness trackers. Now, before any lesson, you're going to see this notebook configuration instruction, and it's going to tell you to run this command. Let's take a look at the includes configuration file so that we can get an idea of what's included there. All right, so in this file, we've pulled out some of the basic logic that we're using to keep everything tidy in your Databricks workspace. So, for example, we're creating a username for you here. That's going to be a string, and then your first and last name separated by an underscore. I'm going to type Kate_Sullivan because that is my name. In the next command, you can see that we are using that to create a health tracker variable, and that health tracker variable just holds a string that will become our data path. So you can see that's going to be in DB Academy with your username, so that you have a unique location to write to, plus Lakehouse with Delta Lake DD, plus health tracker. We're also going to use your username to configure a database. So we're going to create that database if it doesn't exist, and we're going to set our program to use that database. The last thing we're going to do is import some utility functions. This will pull code from a different notebook, and we'll take a look at those utility functions in a moment. Now we'll go back to the ingest raw notebook, and now when we run that includes configuration file, it's going to run all the commands that we just saw in the previous notebook and define our data paths and configure the database and import utility functions, all scoped within this notebook so we can use them. Okay, in our next command, you're also going to see again in later notebooks, because we're going to want to make this course idempotent. So that means you can come back to this course no matter where you stop, and you should be able to run all of these files, because what we'll have done is run this cell so that we remove the files that are held in the health tracker pathway that we defined, and we're doing that recursively. And then we're also going to remove any tables that we'll create later. So health tracker process is a table we'll create later, as is health tracker gold aggregate heart rate. When we run this command, it drops all of those tables and it gets rid of the records that we had previously. So now we're ready to go ahead and retrieve our first month of data. For that, we're going to use a utility function, retrieve data, to retrieve the files that we're going to ingest. Notice that this function takes 3 arguments, year, month, raw path, and the optional argument is late. Let's take a look at that utility function file we talked about earlier to see what this function actually does. So here in the utilities file, we can see that we've got a bunch of different utility functions. Now, when you run this utilities file from a different notebook, it defines all those functions within the scope of that notebook. This one defines a base URL, which is just a location in cloud storage. And we're going to be focusing on the retrieve data function, which takes year, month, raw path, and is late as arguments. It looks like that just parses those pieces together to create one long file string, because we know that the string name or the file name matches a certain pattern. Let's go back to ingest raw, and we'll run that function for 2020 month 1, 2020 month 2, 2020 month 2 for some late data maybe, and 2020 month 3. So we want to land this in the raw directory. So we're going to use that health tracker destination that we set up earlier and add the part of the file path named raw. And that's the piece that is going to move that into our Databricks file system. We are going to want to test our data later. So at this moment, I'm just going to run this to establish the expected file name that we've got. And we'll be able to run a test on that later. Let's also just take a quick look at the files that are in the raw path now. We're using the Databricks file system to temporarily store the files that we'll be using for this course. Notice that the path here matches the path that you defined in the configuration file earlier. So you can see here the whole file name that includes your username, and all of these files are in the raw directory. You can and should write unit tests for your code that is going into production. So to give a demonstration here, we just included a simple assertion statement. No, we wouldn't typically have a print statement here. We're just using this as an example. So we've got this assert and then a fill this in, and then a little bit of a list comprehension. So let's go ahead and grab that file name that we established earlier. And we want to check and make sure that that file name is in the list of files that we just looked at. So we'll get that health tracker raw directory that we created and loop through that and see if that file is there. And it is. So great job. All right. In the next lesson, we're going to be reviewing and visualizing data. See you there. Hi, welcome back. In order to navigate to the next lesson, you can use the Workspace menu on the left side nav bar. That'll open up our menu with all of our notebooks, and you should click on 01 Review and Visualize. And that'll open our next notebook. We want to make sure that we are attached to a running cluster, as always. Okay, great. So now we've set up our system so that it moves raw data from its source into a file path in our data lake that we're calling raw. Throughout these notebooks, we're going to try out what it looks like to move data through a whole system. So here, we're going to be looking at a mock IoT sensor data set, just for demonstration purposes, that includes heart rate data that is measured by a health tracker device. And what we're actually trying to simulate is how data would move into our system from a streaming source. So before we get started, make sure that you run that includes configuration cell to set up our utility functions and our data paths. And now let's take a look at this data. So in a typical system, iFlux event data will be delivered to the system via a stream processing server, like Apache Kafka, for example. For our purposes, we've made this data available for download from static files. And the commands we ran in the ingest raw notebook are used to download the data into our system and are intended to simulate the arrival of this high flux event data. So we've got all of these transactions that we're processing and we're pulling into the system on an ongoing basis. The files that look like this are multi-line JSON files, and they resemble the strings that are passed by Kafka. Okay, and now let's take a look at the schema. We can see that we have a name, which is a string, a heart rate, which is a double, device ID, which is an int, and a time, which is a long. Now, it's pretty easy to see that checks out visually. The time string looks like it's probably a Unix timestamp that we can convert pretty easily into a timestamp later on. Great, so moving on, it looks like we have found our first to-do in this notebook. We're going to load the data as a Spark data frame from the raw directory. This is done using the .format JSON option, as well as a path to the load method. So we can see here we've got a file path, and that's made up the health tracker string from the config file, plus this additional file name. And that's going to create a health tracker data frame. We want to get this .format JSON and put that in the fill this in area instead of that. And then another option we need to include the load method. Whoops. And in that, we're just going to put that file path name that we established. Great. Okay, excellent. If we click on that, we can see that we've got all of the fields that we were expecting. We've got the name is exactly what we expected, and it is in fact a data frame. Great. Let's move on to visualizing data. Strictly speaking, we don't necessarily have to do this, but the display gives us a good look at the data that we're working with. And it can be helpful to just sort of get a sense of what kind of values you have. So here I have my data frame wrapped in a display command. That's going to show me my data in a pretty table. I can see I've got a bunch of records. And now I'm going to create a visualization from that. So here we've got the button that shows us our raw table. And right next to that, when you click on that, that's going to create a visualization immediately. So let's click on plot options so that we can configure that to something that's a little more useful. You can see the options are listed out for us in the next cell, so you can refer to those as you're building this plot. But our keys are going to be time. In series groupings, I'm going to want device IDs, and then for values, we'll have the heart rate. On these other items, we want the aggregation to remain sum, and we can leave the display as a bar chart. Just looking up here, we'll see a quick preview of what we're going to look at. That looks right, so let's click confirm. All right, that's going to run, and it's going to give us a visualization of the data we're working with. So let's see what's going on here. I can see right away that there are a couple of negative values, and that's surprising, right? Because this is, after all, heart rate data, so it seems like something is probably wrong there. We could check that out, maybe some broken readings. I can also see that these exist these are sort of cyclical, right? There are periods of higher heart rates, and then there are periods of lower heart rates, so that might be, wakefulness and sleeping. You can see some elevated periods of heart rate activity, and so there may be some exercising, right, that's happening during those times for different people. Okay, great. And also I can see that I've got 5 different sets of data. I don't know if or 5 different device IDs that we're working with. When you read in the data, you probably noticed that it represented 1 month of data. So it looks like I've got 5 device IDs and 1 month of data for each. And with that, it looks like we are ready to move on to our next notebook, where we will be creating a parquet. Hi, welcome back. You should have navigated to the Create a Parquet Table notebook. You can do that using the Workspace menu in the sidebar and just click on O2, Creating a Parquet Table. All right. As usual, we're going to make sure that we are attached to a running cluster and we run that configuration cell to set up our data paths and utility functions. Another thing we have to do in this cell is run this command to reload the data to a data frame. So the data frame that we just defined is only scoped locally to the notebook we were working in. We're just going to run that data frame creation statement using the file path to create that data frame in this notebook. You can see it's the same data frame, we've got the same schema. Okay, so now that we've got our lesson setup done, we'll move on to this first step, which we're going to make this notebook idempotent, just like we did in the previous notebook. The reason is that we want to be able to come back to this notebook and be able to run it again. So it's important that we just keep this space clean. So from our Databricks file system, we are going to remove the health tracker processed file. Note that that may not exist for you yet, right? If this is your first time going through the course, it won't. But we'll make that a recursive, we'll make that function recursive so that it goes back and deletes everything in that file path. The other thing this is going to do is just drop the health tracker table if it exists, health tracker processed if it exists. So let me give you some clues into what we're about to do in this lesson. But I want to note also that throughout this lesson, we are writing files to the root location of the Databricks file system. And we do that because the Databricks file system is easy to use for this purpose specifically, right? We can be reasonably sure that you all have access to the Databricks file system, and we can just write to there and then clean it out when we're done. In general, you would be writing to your cloud object storage because, as you'll recall, our big goal here is we are incrementally cleaning files along the way and creating a few intermediate steps. We're looking for raw, we're looking for a sort of more processed table that we'll be working with, and then later on we'll create our polished tables. So as the title would lead you to believe, in this lesson we will be creating a parquet table. And I want to be clear that that is not part of what you would have to do if you were just going to set about building a pipeline to transform your data and using Delta Lake. We do that specifically here because we want you to have the experience of creating a parquet table, and we can start to see some of the problems that may emerge. And then we also want you to have some experience converting a parquet table to a Delta table, which incidentally we'll be doing in the very next lesson. So let's get started here with creating this parquet table. So we've already landed our raw data from the streaming source, right? And we're not going to mess with that too much. We don't want to mess that up. That is just like the place where all of our data is going to land. But we are going to need like an intermediate table so that is somewhat processed that will feed our later data mart sort of gold level tables later on. So in this step, when we created a parquet table, we're going to transform this data. We can see that we're using from Unix time a couple of times to change the time column to both a date and a timestamp. Heart rate we're going to leave as it is, name we're going to leave as it is, and then we want to cast device ID as an integer, and we want to alias that to p_device ID. This is sort of a sneak peek into what's about to happen in like maybe the next cell in this lesson. We're naming it that way because device ID is going to be our partitioned column, right? We understand that later on as we're querying the data, it may be useful to pull just a single device ID. So it may be useful to have that have all of this data split up into directories so that I can pull data from just those files later on if I want. All right, let's take a look at this to do. So I've been given some transformations in the instructions to apply here. In this first one, I am going to transform the time column. I want to cast that as a date, and the alias has been filled in for me. I'm going to transform the time column again, and this time we want to make it into a timestamp. Okay, heart rate and name stay the same, and then I want to grab that column device ID, and I want to cast that as an integer. And I want to give that p_device ID alias. Great. So that's the thing that's doing the transformations, but I want us to notice before we move too far that we are actually working with a function, and the function is to process health tracker data. It takes a data frame and it returns a data frame. Now this is best practice because that means that we have to write this series of transformations once. We know we're going to be receiving more data from this streaming data source, and if we want to process it all in exactly the same way, we can just use this function later on as the data arrives. Okay, so we have our process data frame, and that is calling the function process health tracker data, and we're passing in the data frame health tracker data 2020_1. Great. So when we run that, we'll end up with that new process data frame that has the schema we would expect. Excellent. All right, so let's move on to writing the files to the process directory. As promised, we are going to be partitioning the data in this step. It is best practice whenever you can to use partitioning when it makes sense for your data. So we've got all these device IDs. It is very likely that we will want to grab information about just one of those device IDs in the future. So we're going to partition by that. And to tell everybody that we have partitioned by that column, we're just going to throw that p_ in the front of the device ID name, and then anyone who's looking at it could say, oh, that's the partition column. So queries that filter on a certain ID, for example, might be super fast because we can avoid reading a lot of unnecessary data and only pull in data that we really definitely need. So let's go ahead and look at these instructions and see what we've got to do to write out this process data frame. All right, so this says we are going to use .format parquet, right? Well, that makes sense because we're writing a parquet table. And then we also want to partition by device ID. So I'm just going to grab that from the instructions and paste it right in. And then we don't directly give the partition by syntax, but it looks like this. And we'll put p_device_ID in there. And then we want to save that as our health tracker base file name plus processed. So now we're going to register that table in the metastore. First, we're keeping this idempotent by dropping the table by that name if it already exists, right? We don't want to get into a situation where we try to run this command a second time and we get an error message. Then we're going to use Spark SQL to create that table with that same name. We'll specify that we're using parquet. And then we can also specify the location we want to take the data from, and that is our health tracker file name /processed. Great, so we run that and we can see that command was successful. Now let's verify the parquet-based data lake table. We're going to do that by just performing a count. We just want to make sure that all the records that we had in that data frame made it through to this registered table, and oh no, it looks like we've got a 0 count for this table. What could have happened? It looked like everything was successful. Well, as it turns out, we will actually have to register these partitions in the metastore. So we've created a partition table, and right now, Metastore is not looking anywhere past that initial folder. So in our health tracker process folder, we've got 5 separate partitions, one for each of the device ID. And then inside each of those folders is where we have the actual records. So if we just register these partitions with the metastore will be able to count all of our files. To do that, we are going to use this msck repair table command. That will register the partitions in the Hive metastore. You can learn a lot more about how this command is used by checking in the docs. Also, just to mention, you will frequently see some notes in our notebooks to check the docs. We encourage you to read through the docs about any of these commands. All right, great. So now I have run that. That looked successful. And we want to run another count on this new table. Great. Okay, we have 3,720 files. That makes a lot of sense because remember we have 5 device measurements and we're getting measurements by the hour for 24 hours a day, and we're doing that for 31 days. So 3,720 is the number we expect. Excellent. Great going. We are ready to move on to actually creating a delta table. So please join me in the next lesson. 03, creating the delta table. Okay, welcome back. If you haven't already done so, take this opportunity to open up your Creating the Delta Table notebook and make sure that it is attached to a running cluster, as always. All right, so in this part of the lab, we are going to create delta tables, right? We just made a parquet-based table, and we want to convert that to a delta table. So let's recall from the theoretical portion of this course that a delta table consists of 3 things. We've got the data files that are kept in object storage, like AWS S3 or Azure Data Lake Storage. We've got the delta transaction log that is saved with delta files in object storage. And then we've got a table that is registered in the metastore. That stuff is optional, but we usually recommend it. That's how we are able to query it with using SQL. So we've already got a parquet-based table, so we've actually already got those files that are in object storage, but we'll be adding the transaction log and registering in the metastore. Let's run our configuration file to make sure our data paths, database, and utility functions are all set up. Now, when we go to create a table, right, we should understand with Delta Lake you can create tables a couple of ways. One is ingesting new files into a delta table for the very first time. We would specify with the Spark data frame writer that we would be using a format delta, or by transforming an existing parquet-based data lake table to a delta table. And that's the thing that we're going to work on first here. So this is another note about the DBFS. We can skip that for now. But we are going to just take a look at some of the table that we've got here. So before we convert the health tracker process table, let's use the describe extended command, and that's going to tell us a little bit of extra information about this table. Describe would tell us just like the column names and the data type, but if we scroll down in this describe extended command, we can see a little bit more information, including which of these are the partition columns, which we don't really need, remember, because we've got that p_device ID, so everybody knows that that's the partition column. And then we can also see some detailed table information that includes the database that we're working in, the actual name of the table, and if we scroll down just a bit more, we can see that the provider here is listed as Parquet. So this is a Parquet-based table that has been verified, and we know pretty much everything else that is in here. And that's great. So we verified that. Let's set about to converting the existing Parquet table to a Delta table. We're going to do that by converting the files in place to Delta files. And what that conversion does is create a Delta Lake transaction log that tracks those associated files. So we will first create the string Parquet table, and that's going to be parquet.our file name. And we will also define a partitioning scheme here. and we're just registering that the device ID is the partition column. Then we'll use the convert to Delta method. Great. All right, so it looks like that was successful. Let's go ahead and register this Delta table. So at this point, the files containing our records have been converted to Delta files, but the metastore hasn't been updated to reflect the change. So to change that, we're going to re-register the table in the metastore. We've got to use this drop table if exists command first, because remember, we actually do have a table in the metastore that is registered as health tracker processed. And then instead of using parquet, we're going to use Delta. So we create table with that name that we were already using. We're going to do that using Delta, and we've already rewritten the files so that they are Delta files. So we'll point to that same location where we've got our health tracker file name and processed. Great, so now that we've got our Delta table, I actually I want to change the table a little bit to add some column comments so that as people use this table, they will already know what information is included. Right, so I'm going to use this alter table command on our health tracker processed table. And I want to include some additional information on each of these columns so that people will just be able to see it without reading in all of the data. They can just use the metadata to better understand what information is in this table. So here I'm going to include the format that folks should expect for the date. I'm keeping the timestamp listed as timestamp, and the heart is double, but I do also want to tell people that the names are listed as format, first name, space, last name. Also, I'm including the device ID range, so we know that we've got ranges 0 to 4 here. So these comments are just going to travel with the table. So anyone who uses the describe extended command, for example, or even just the describe command. Oh, I had forgotten to run that. Whoops. So after I run the alter table command, and then I run that describe extended command, even if I was just running the describe command, these comments would show up in those. But I'm going to run the describe extended command for two reasons. One, we want to see that the comments show up. Right, that's just like we might expect. It's still showing us our partition column. And then we can just verify that the format here has been changed to Delta. So this is our new Delta table. This is still in that same location, right? We have converted those files in place. All right, excellent. So let's do a quick count just to double check our records, make sure everything is as we expect. I think we're still expecting 3,720 of them, and that's what we've got. Note that we didn't have to do a repair table command. The metastore is aware of our partition columns and could count up all of our records. Okay, great. So now we've got our process table. It is in Delta. And we are ready to create a new Delta table. So we're going to take some of this data from our process table, and we're going to move it to our gold level table, which remember is sort of like a data mart kind of a table. And so it's designed to fit a very specific use case. In real life with real data, you might have you might be making multiple gold level tables that are all sort of feeding from this intermediary processed table. The information in this kind of table could be used to populate a dashboard, or the query used to create the table could be issued against the health tracker process table nightly to update the dashboard for the following business day, for example. All right, so another move toward idempotency. If you run this notebook, you will have a health tracker gold path. We want to go ahead and just remove all the files that are there in case you already ran it. In case you already ran through this lesson before, we want to make sure you have a a clean go of it this time. And now we're ready to create an aggregate data frame. The subquery used to define the table is an aggregate query over the health tracker process table. So we're going to create some summary statistics for each device. So we use that health tracker processed. We're going to get the average heart rate, and we're going to get the max heart rate as well as the standard deviation. And those have all been aliased to some column names, so it will make sense. Excellent. And now we can go ahead and write the delta files. So we've got that data frame, and we're going to write, and instead of some other format, we're going to just specify that the format is delta. We're going to overwrite anything so that it overwrites any files that already exist. And we're going to save with our file name, health tracker plus gold, and then health tracker user analytics. Excellent. Now let's go ahead and register that table in the Metastore. So we want to first drop the table if it exists, specify using delta in the command when we create the table, and give the location to get the data from. Excellent. And now let's just get a look at our data. So we run this display, and we can see we've got all the commands we expect. The average heart rate, max heart rate, and standard deviation. We can make a visualization here, just the same as we did in that first or second lesson. And we're going to arrange the keys by device ID. The groupings are going to be values, max heart rate, and standard deviation heart rate. So that's all going to show up together. Great, and now we've got a nice little visualization comparing some key statistics from our health tracker table. So just to review a little bit, so far you have made contact with the streaming source, landed that in some raw data files, processed some of that data to keep it in an intermediary table, and then aggregated over that table to create like a gold data mart kind of table where you would use visualizations and dashboarding to communicate. So now we've done this little bit of practice with creating a streaming pipeline. Let's see what it's like to batch write to a Delta table in this same system. Join me in the next lesson. Batch write. Hello and welcome back. To navigate to our next lesson, you can use the Workspace tab. That'll pop out this menu. Click on Batch Write to Delta Tables, and that will open our new notebook. All right, so far you have been working with streaming data. And in this notebook, we're going to see what it's like to append files to an existing Delta table, right? So sometimes we'll want to stream data in and also batch write to a Delta table. And we can do that all within the same system. There are two patterns for that. One is appending files to an existing directory of Delta files. That's the one we're going to work on now. And then merging a set of updates and insertions, which we will work on next. To get started, let's run this configuration file and actually, the first thing we need to do is attach to a running cluster, and then we can run the configuration file. And then I'm also going to run this. This is new, includes main Python operations. I'm going to go ahead and run that, and then we'll just take a second to inspect what that's doing. So we have includes main Python operations. Okay. So it looks like we've got a bunch of imports up here, and then we've got this thing that should actually look familiar to you, right? We have created, in a previous lesson, we created a function to help us process the incoming data. Here, we have something very similar, right? We are going to process that health tracker data. It takes in a Spark session and a data frame. The one we worked with before just took in the data frame, but we'll take in the data frame and we return, notice, our columns that have been converted to time and device ID and a timestamp and a date. So all the stuff that we had, before. So this will end up matching the schema of the process table that we've been working with. So anytime we're getting this new data, we can just run that function. All right, let's get back into the batch write notebook. So we've got that function all defined for us. So we'll see where we're going to use that. So our first step here is going to be to sort of go back to the beginning and just load new data into that raw file path that we are working with. So we're naming this file path, health tracker plus raw, and then the name of the file. This time it's from 2020_2, and that's in JSON format, and we're using the file path to load that up. This makes a lot of sense, right? This is the types we've been working with. Now we can transform that data. And it's really simple, right? Because we already created that function that transforms the data. So we want to perform that same data engineering on it. So we'll use remember we're using from Unix time, and we're converting the column to a timestamp and creating a date column and all that. So our process df, when we run that, will just run this data frame through that processed function. And that's going to give us all the schema that we expect from the previous data that we were using. Excellent. So now that we've got that same schema, we can append that data easily to the health tracker process data delta table. So we're going to use the .mode append method here. And we're not really changing anything about the actual table, right? We're just appending some data, and we don't need to perform any action on the meta store here. That data is just going to get added to that table. But how can we check what we've done? We can actually view the commit using time travel in Delta Lake. You can query an earlier version of a Delta table using this feature. It makes use of the Delta log to find different changes to your or different versions of your Delta table. So the data as of version 0 is the initial conversion from the table from Parquet. So when we time travel to that, right, we specify the option version as of 0, still in format Delta, and we just put in the count right in here. We can look at all those records, and remember we had 3,720 records then. Great. Next, we can take a look at what's happening on our current table, or our most recent version, by not specifying a version at all, right? When you don't specify a version, it just shows you the latest version of the table and includes the new records that have been added. Let's just take a minute to review what we should expect, right? We're looking for data from January 2020, that has 31 days, and February 2020. That actually had 29 days because February 2020 was a leap year. So that means we're looking for 5 devices over 60 days, right? 31 and 29. And then each of those devices is reporting once an hour for 24 hours. And so that should give us a grand total of 7,200 records. Let's run this, see what we get. Oh, 7,128. All right. So then we know now that we're missing 72 records. Let's go on to the next lesson, and maybe we can figure out a way to explain that. Our next lesson is exploring the SSOT, single source of truth. Hi, welcome back. If you haven't already done so, please navigate to O5, exploring the SSOT using the Workspace tab on the left side navbar. All right, so in a previous lesson, we used Apache Spark to perform a batch update of the health tracker process table. And when the process was complete, we counted the number of records in the table and discovered that some of those records were missing. The absence of records from the last few days of a month shows a phenomenon that may often occur in a production data pipeline, late arriving data. Delta Lake allows us to process data as it arrives and is prepared to handle the occurrence of late arriving data. This is one of the reasons it's so important that we get to use the same process for This is one of the reasons it's so important that we get to use the same system for batch and streaming workloads. All right, so let's get started by making sure our notebook is attached to a running cluster and then running our configuration cell. Great. Now, we'll have to count the number of records per device. So here's what we've got our to-do cell. Let's read through and see what we need to do. Let's run a query to count the number of records per device. Recall that we'll need to tell Spark that our format is a delta table, which we can do within that format method. And additionally, instead of passing in the path as we did in previous notebooks, we're going to pass in that health tracker variable that we defined. And finally, we'll do a group by and an aggregation on our device ID column. All right, so we know that the format here is going to be delta. And we know that the variable we're using that holds most of that string, that is our file location, is health tracker. We're adding process to that. That's going to be the tail end of that file name. And we're grouping that by device ID and then just counting all of the records for each of those devices. All right, awesome. So that's pretty clear, right? There's one device that is missing a few records. That's device number 4 there. So let's see what we can do to recover that. First, we can use a visualization to spot where these missing records are occurring. So the table doesn't really give us all that much information. It's pretty hard to look at. It'd be hard to spot using just that. Let's go ahead and use one of those built-in visualizations to get a better look, a more descriptive look at what has gone wrong. Okay, and we'll just configure that up. We're going to want to show the date as the key. And then we're going to want to show the heart rate as the values. And instead of sum, we'll use a count. And we can still use a bar chart. Oh, and in order to see both of those device IDs, we're going to use that as our series grouping. So that will run that query again and deliver our visualization. Okay, it's pretty clear, right? We've got even data and for most days for both 3 and 4. We didn't have to look at 1 or 2 because those are all the same, right, as 3. We know data is only missing from 4. And it looks at, like, at the tail end of the month there, we're missing a few records. Great. So probably that what we talked about, that late arriving data, that seems to be what has happened. Okay. So there were also, now that we're thinking through some of the things that are wrong with our data, remember we did see some broken readings, right? When we initially loaded the data into the health tracker process table, there were some of those negative readings, which, obviously can't happen when you're taking heart rate data. So let's also investigate a little bit around those broken readings. Here, we're going to first create a temporary view for the broken readings. So we do that to figure out where the heart rates are less than 0. Okay, so let's take a look at our to-do here. We've got spark.read format as delta. We're loading the path name, heart rate, and date. Yes. And we're wondering where the heart rate column is less than 0. When we know that, we're going to group that by date and count up all the heart rates, and we're going to order that by date. Excellent. So that's a view that just holds dates and it holds the count of heart rates that are less than 0. Let's take a look at that view. Okay. All right, so just looking at this data, I guess we've got, one or two sort of broken readings across a certain number of days. It's not that easy to get like a good sort of rule like we had in the last one where we just saw we were missing 3 days of readings. So let's just count up the number of records that have negative heart rates, and we can see that there are 60. Okay, so we have looked into our single source of truth and we've seen a couple of problems. Now that we've identified those problems, we can start the process of fixing them. Go ahead and take a short break, and we'll start on that when you get back. Hi, welcome back. If you haven't already done so, please navigate to the Upsert into a Delta Table notebook. You can use the Workspace tab to pop out this menu and then click on that to open up the notebook. Great. As always, we need to make sure that this notebook is attached to a running cluster. So go ahead and select your cluster. And then let's focus in on what we're going to get done in this notebook. So we want to upsert into a Delta table. And that is, we are going to repair some of the records that we saw using something called an upsert. So recall that in the previous lesson, we identified two issues with the health tracker process table. One, we're missing 72 records. And two, there were 60 records that had broken readings. In this lesson, we're going to go ahead and repair the table by modifying that health tracker processed table. So we want to make sure that we can add the necessary readings, and we want to make sure we fix anything that was broken. Okay, so let's go ahead and get started by running that configuration cell. And remember, we're going to be using that function that we investigated last time, so let's run it so it's scoped to this notebook. Great. All right. So there are generally two patterns for modifying existing Delta tables. We could append files to an existing directory of Delta files. We've already done that. Or we can merge a set of updates and insertions. So in this lesson, we're going to do that second thing, and using something called upsert. An upsert is the portmanteau of the words update and insert, and that says exactly what it does. An upsert will update records where some criteria are met, and otherwise it will insert a new record. So when upserting into the existing Delta table, we use Spark SQL to perform the merge from another table or view. The transaction log records that transaction, and the metastore immediately reflects those changes. The merge appends both the new and inserted files and the files containing the updates into the Delta file directory. The transaction log tells the Delta reader which file to use for each record. Okay. So the first thing that we're going to do is try to prepare some updates for the data frame. We'll start with the broken sensor readings. That is, those readings that were less than 0. We'll want to interpolate using the value recorded before and after for each device. So that just means that we are going to look at the values that were collected around that broken data, and we're going to use those to make an estimate about what we expect those broken readings should have been. We'll use the Spark SQL functions lag and lead to make that calculation. And we'll write that into a temporary view called updates. Okay, so let's take a look at this to do. So we've imported a window object and the functions that we're going to need. We know that our table is going to be partitioned by device ID, and we are also ordering that by date. So we're creating this interpolated data frame, and we're going to use that to make the upserts later. So we're selecting all of the columns, and for every row in the heart rate column, even though we're not going to use all of these values, for every one of them, we are going to find the previous heart rate for the day and the later heart rate for the day. And then we're going to create two new columns, previous amount and next amount, that hold those values. Then we're also going to include the name and device ID. So notice here we have two new columns, prev amount, that's going to be the previous heart rate from any record in the table, and the next amount, which will be the following heart rate for the record in the table. Okay. So we've got that new table that includes all of those interpolated values, but we're not going to use them all, right? Because we don't want to throw out the data that is good, right? We want to just repair the records for those broken readings. So let's create a data frame that has all of our updates. To do that, we're going to specify exactly where the heart rate is equal to, is less than 0. And that's going to return only those values that have only those rows that have the broken readings. And instead of including the actual heart rate here, right, we're going to use the average of the previous and the next values. So that's the interpolation, right? We're making up that value based on the heart rate that was happening right before, and then the heart rate that was reported right after. That's a more reasonable estimate than just saying, just making up, some other number or taking the average of all of the heart rates. Okay, so we've got our name column also and our device ID. Great. Okay, so look at that. Now we have a schema that matches the schema that we've been working with in our health tracker processed table. And all of these updates all have positive values now. All right. So now let's view the schemas of the updates data frame and the health tracker process table. We can use print schema to do that. In this, it looks like we just need to fill in the format for this data. We know that we're working with Delta. And when we call print schema on it, it gives us the schema for both. So we've got updates at the bottom and the health tracker processed at the top. And those match. So excellent. Now, let us just perform a count on the updates data frame. Recall that it should have the same number of records as the sum that we performed in the broken readings view, right? And that has got 60. Excellent. So we had 60 readings that showed up in that broken readings view, and we've got that same number now. So it seems like we're on a good track. All right, great. So on to the next problem. Let's go ahead and prepare those inserts for the data frame. It turned out that the expectation of receiving those missing records late was correct. Those records have been made available as the file health tracker data 2020-0201. Great. So this has our same data. This has our same schema as our raw data frame. I'm just going to comment that out. And then in order to figure out what we're looking at here, we're just going to go ahead and include a count. Okay, and that's the 72 records that we were missing. This is all coming together. So we'll remember that this data is coming into our raw path, and we're going to need to apply those transformations to make it into the may have the same schema as the processed table. So we're going to transform this data using that function that we created in the file that we looked at earlier. We're going to take that health tracker data 2020_2 late data frame and pass it on into process health tracker data. And when we do, we get the schema that matches our processed table. Great. Our heart rate is double, name is string, and we've got a device ID that is an integer. Excellent. All right, so let us print that schema to take a look at that. Okay, so all the records that we're working with that we want to repair as an update or an insert should have the same schema at this point. So let's go ahead and union those data frames just so that we can get a single collection of both updates and inserts, right? Because we are creating that upserts data frame, and that's a combination of both of those things. That came through, so that will include all the records that we from both of those individual sets. If we take a look at that schema, that is going to match our process table perfectly. So now we actually have to perform the upsert. We We upsert the data into a delta table using a merge operation. It's similar to the SQL merge command, but it has some added supports for deletes and other conditions in updates, inserts, and deletes. In other words, the delta table command .merge provides full support for an upsert operation. Let's jump right into this code and we'll see what is going on. All right, so let's just start with the imports at the top. We're creating a processed delta table, and that delta table is pointing to the files that are at that health tracker processed pathway. Okay, good. Now I'm going to skip the stuff in the middle for right now, and just we're going to come back to that later. That's some specifics about what we want to do, but let's just try to figure out what's going on in the bottom here, like what we're actually trying to get done, and we'll match that up. So we've got that processed delta table, and we're going to alias that as health tracker. And in that, we're going to merge the upserts data frame, which we're going to call upserts, using the rules provided in our update match. Okay, so let's look at the update match. We've got health tracker. Remember, that's the alias for our process table. Health tracker.time should equal upserts.time. So we want to make sure that the timestamps for these two things are the same. And we also want to make sure that the health tracker device ID is the same as the upserts device ID, right? So remember, the files that we want to update are the ones where we have interpolated that value, right? Interpolated the heart rate. So we're just going to update there. So when those two things match, this is saying go ahead and do that update and make that heart rate equal the upserts heart rate. Then, once those are done, we'll have some collection of files that have matched, and those heart rates have been updated. But then we have to also handle the other instance of cases that don't match. So this is, remember, we have values that are completely new. So when we're trying to add those old values, they won't have a timestamp that matches, right? So when they don't match, we're going to just insert those values because those are brand new to the system. So when we execute that, what should happen is that those that can be updated, right, the ones with the broken records that have found their matching timestamp and their matching device ID should be updated, and the inserts should just insert those new columns from the upserts table. Or sorry, not the new columns, the new rows, the new records from the upserts table into our existing delta table. Okay, so now we got that. We can go ahead and execute. That's going to take a minute to run and write in those new files. And then to verify, we're just going to view the commit using time travel. So we're going to specify the option version as of 2. Remember when we time traveled to version 0, we saw just that initial commit? If we traveled to version 1, we'd see those same records, but remember we altered the table to include the comments. So that shows up in the version history. But when we time travel to version 2, we can actually see the first 2 months of data minus the 72 records that we're missing when we discovered that. Okay, so when we run that, we get 7,128 records, just like we expect. And now, let's go ahead and just count the most recent version to see how many records we have after that upsert. Remember, when we count the most recent version, that's just going to give us our table that has all of the information added to it We can travel back in time, of course, but if we just call the table without any time traveling, then it just gives us our complete record. So now we have 7,200 records, and that is just what we expected. It's good to check, right? Because we want to make sure that we didn't add any records when we were doing those updates. You may want to view the history of the health tracker process data. That is, all the commits that you have made to the process delta table since it has been a delta table. So that includes information like the user and the operation that was performed, and the timestamp when it was performed. So that has a lot of super useful information in it that you can use to track down any problems, right? There we can see the creation of the delta table in that replace columns. That's where we are creating comments. And then we had an append that added some records to that table. And then finally, we merged in some late arriving data and we updated some of those records. Wait a second, a second upsert? Oh yeah, when we just performed that first upsert and we inserted that late arriving data, we didn't examine that first to see if it had any broken readings in it. And unfortunately, it did. So we've got to go back and we have to find more of those broken readings in our table, and then we can perform a second upsert to get rid of them. I'm going to give you a second to look this over if you haven't already done it, but this should look pretty familiar, right? We're using the same kind of format to create our broken readings view for this next upsert. So we're going to load from the health tracker processed path, where we only need heart rate and date. And then we want to make sure that we select only the heart rates that are less than 0. So we'll write a column heart rate less than 0. And then we also want to make sure that we are grouping by the date, right? We're going to get the number of broken readings per day. Then we'll count up the number of broken readings each day, and then we'll order by the date so we can organize our output a little bit. Okay, excellent. So now we've created a temporary view that's called broken readings, right? We just are giving a name to that so we can reference it. Let's take a look and just make sure that these are in fact new broken readings. So we want to find the heart rates from broken readings where the date is before February 25th. Okay, none, right? Because that represents all the things that we fixed. But remember, we inserted data that was past February 25th, right? That's where our late arriving data was. So great, no broken readings before February 25th, 2020. And then we're just going to perform a count on the updates view. We don't actually have to redefine the data frame. It's just going to get pulled when any action is triggered. So performing a count on the updated table goes ahead and just returns our current set of results. So now, let's go ahead and perform the upsert on the health tracker processed table. We're using the same rules as we used before, right? So we don't necessarily need to redefine anything. And now we can use the same merge settings as we used in the previous operation. All right, so now let's sum the records from that broken readings view one last time. And we've got none. All right, excellent. So now we've seen how we can change some specific values with Delta Lake. What happens if our whole schema changes, if the whole way we collect data is different? See you in the next lesson. Hello and welcome back. In this lesson, we are going to work with schema enforcement and evolution. To navigate to that notebook, click on the Workspace tab to pop out this menu, and then click on the Schema Enforcement and Evolution notebook. And voila! Okay. First, we're going to want to make sure you are attached to a running cluster. And then we are, as always, going to want to make sure that we run that configuration file, set up all of our data paths and stuff. And then let's just take a minute to think through what we are going to want to do in this notebook. We want to know how to work with evolving schema. And at Movio, we have created this data pipeline, and we've got a couple of functions in place to process the data as it comes in, and data can flow sort of seamlessly through the system, which is great. However, it's not uncommon that the data being ingested into your system will evolve over time. So in this case, we're going to imagine that the health tracker device that we've been working with has a new version available, and the data being transmitted now indicates which type of device is being used. So let's go ahead and take a look at our data. We can see it looks a lot like the data that we were looking at in the previous lesson, except we've got this new column device type, and that is telling us that we are using version 2 of this health tracker. Okay, but on examination, everything else is pretty much the same, right? This data is still streaming in. We've got most of our columns and types are all the same. Just this one extra piece is what we've got. So let's see how to work with this. We'll begin by loading the data from the health tracker in the 3rd month. We're still using format JSON. We've got the device type that is a string. That's new. Then we want to transform the data, and we want to perform that same data engineering that we did on all those columns that stayed the same. So we've still got the same data frame in, data frame out function, right, where we're processing the health tracker data. And then we're just going to include device type as our next additional column. So now we have our new process health tracker function is going to take a data frame that also includes device type. So when we run this on our new data, we're going to get our processed data frame. Now, let's go ahead and just add that data. Oops, gotta run that. Now let's go ahead and we'll just add that data to the health tracker processed delta table that already exists using the mode append. We're gonna wrap this in a try except because I'm not sure it's going to go through, and look at that, it doesn't. We find that a schema mismatch has been detected. And in many cases, this is exactly what we want to happen, right? We want to avoid our data lake, our single source of truth, from being corrupted, right? And that means that we want data to get checked in as it's ingested, and if it's not the kind of data that we expect, it's helpful for this to throw an error. But in this case, we've got mostly everything that's exactly the same, and we've just got like this one additional column. So if you are conscious about it, right, you can make the decision to set the option on merge schema to true, and then that will enable schema migration. So if we look at this, it shows you in the error message, it shows you the table schema, and then it shows you the new data schema. And it also just gives you this tip that if you want to enable schema migration on the data frame writer or data stream writer, you can actually just set that configuration option. Here's another case where we're pointing you to the documentation. Documentation is really good around this, so definitely please go check that out if you have if you have questions about it. So now let's dig into what exactly is schema enforcement here. So this is a safeguard in Delta Lake that ensures data quality by rejecting writes to a table that don't match the table's schema. As I said earlier, that's a good way to prevent corrupt data from entering our tables unknown. Schema evolution, however, is a feature that allows users to easily change a table's current schema to accommodate data that's changing over time. Like in this case, we're adding a new version. We didn't account for a new version at the beginning. You can just set schema evolution to accept this new column. Most commonly, it's used when performing an append or overwrite operation to automatically adapt the schema to include one or more new columns. So in the next step, we're going to append the data with schema evolution to the health tracker processed Delta table. And to do that, we'll use the mode append. All right. So here we have another to-do item. So on our process data frame, we want to use the mode append as mentioned in the instructions. We're also going to set that option merge schema to true. That's when we're writing. And then obviously the format's Delta, and we are keeping the same file path. Excellent. Let's go ahead and verify that commit by reading the table. Okay, so now we've got 10,920 records. That makes sense. That's about 1 new month of records. So great. Please join me in the next lab, delete. Hi, welcome back. Okay, so at this point, you have created an end-to-end pipeline. You've gone ahead and fixed up some records that we found in our data. You've created a streaming system, and you've also batch written to that system. We've also practiced a little bit with schema enforcement and evolution. And in this notebook, we are going to practice with deleting a user's records. So navigate to this notebook by using the Workspace tab. And let's think for a second about why we might need to delete a user's records. Well, we're working for Movio, and Movio is a global company, and we need to make sure that we're complying with all the local laws in whatever region we're working in. So we know, for example, that under the European Union General Data Protection Regulation, known as GDPR, and the California Consumer Privacy Act, CCPA, a user has the right to request that their data be expunged from the system. So let's imagine that a user of this health tracker device has decided, I would like my data to be expunged. So we might simply do this by deleting all records associated with the user. Let's get started by running our configuration function, our configuration file. And then let's go ahead and do a delete. We want to delete all records for device 4. So we have that Delta table. And then from that Delta table, we'll just use a .delete operation, and we'll say where the partitioned device ID column is equal to 4. We do that, Everything looks like it has been successful, but oh no, what if we did that by accident? We deleted all the records from the health tracker process table with a device ID 4, but suppose the user didn't actually want to remove all of their data, but they just wanted to remain anonymous in the system. So we only wanted to scrub their name. In this next step, we can use the time travel capability of Delta Lake to recover everything associated with the record except for the user's name. All right, so let's get started by preparing a new upserts view. We prepare a view for upserting using time travel to recover the missing records. Note, we have replaced the entire name column with the value null. We don't want that to be true of all of our users, so we're going to complete the where clause to grab just the device ID where our records are equal to 4. Now, I don't remember exactly where we're at with this Delta table history, so I'm going to go ahead and just take a look at which version we're looking for. And I can see that the version right before my delete operation was version number 5. So I'm going to change this to 5. And then I'm going to create my upserts data frame with a version 5 in format Delta from the health tracker processed data path. And I'm going to use this where clause here, right, where the device ID is equal to 4. Oops, I think you have to fill that in by yourself. And then in that data frame, I want to select the date, time, heart rate. I'm going to have no value as the name column and the device ID. So now when we look at that upsert, we have all of our standard column values, but where we have name, we just have a collection of null values, right? And the only device ID in this data frame is going to be 4. All right, so we can use this new information that has the name values overwritten. And we're going to perform an upsert. So again, let's forget about this part of it for a second. We know we have this processed Delta table, right? And that's taking in data from the health tracker processed path. So in our merge function, we're going to alias that as health tracker, so we have a neat way to refer to it. We are going to merge that with our upserts data frame that we'll refer to only as upserts, and we're going to use the rules provided in update match. So if we look at that, right, we see that healthtracker.time has to match upserts.time, right? We want to use the same, match these guys by timestamp. And then we also want to make sure that the device ID is equal in both tables. So if those two things match, we're going to go through with the update. Then, when not matched, we are going to set our values to these items in the insert table here. I think you actually had to fill this in, so I'm just going to replace that. And that's blank. We're going to just match up the name with upserts.name. Let's make sure that's the right case. Okay, excellent. And so date matches with date, time matches with time, heart rate matches with heart rate. Let's go ahead and execute that. And when we run the process delta table history, we can see that the most recent operation is that merge. Great. Okay, so now let's count the most recent version. When we look at the current version, we want to see 10,920 records. We've got that. And then let's query device 4 to just demonstrate that it looks the way we want it to. So we can go ahead and just run this, and we can see in the name column, null has been replaced every time where his name used to exist. Great. And notice that in the columns that don't have that updated device type, we just have a null value where it should probably say version 1. Okay. So now, how do we maintain compliance in the system if we can always access historical data, right? So we would still be out of compliance because if we just went ahead and looked at an earlier device, we could get the name of the person who requested their name to be completely scrubbed. So let's start by examining that by querying an early version of the table. So if we go ahead and query the health tracker process table version as of 2, we should still be able to retrieve that name because that version hasn't changed at all. Let's go ahead and run this command. And we see, oh, there's his name over and over. Okay, so that's a problem, right? What we can do is vacuum the table to remove those old files. The vacuum Spark SQL command can be used to solve the problem by recursively vacuuming directories associated with a Delta table and removing files that are no longer in the latest state of the transaction log. There is a retention threshold for this, so the default is like we should keep this around for 7 days, but you could keep it for longer or shorter than that, depending on what needs you're satisfying. In this case, you could set it for 0. In this case, we set it for 0 just specifically to throw this error, right? That's a very, very low retention period. And we want to just call out that that may corrupt the state of your table. But if you're certain that there's no problem, you can actually change those settings to retention duration check enabled false. And then it won't limit you to any certain number of hours. Okay, so let's try that again. We're going to vacuum that Delta table as of right now. And then if we go ahead and try to query that earlier version again, we shouldn't be able to see it because we should have actually finally deleted all of these records from the table. Okay, great. So we get an exception here because the Delta cache contains a stale footer and stale page entries, which just means the file is not found. It doesn't exist anymore. It has been completely cleared from our system. Okay. Okay, great. So that's about it for the hands-on portion of this course. Congratulations, you went ahead and you built an end-to-end pipeline for processing data in Delta Lake.
All right, great. So we finished the demonstration portion of this course. So let's go over what we did. As we said, we wanted to talk about Lakehouse architecture and get some of these core characteristics defined. And a Lakehouse architecture offers transaction support, openness, and support for diverse workloads, as well as end-to-end streaming. We've also discussed how Delta Lake provides the key transactional layer on your data lake that can build the foundation of your data lakehouse. In the demonstration, we used fictional Internet of Things data from a fitness tracker company to build an end-to-end online analytical processing pipeline that supports both batch and streaming. And we followed the Delta multi-hop design pattern to curate our data lake as we moved from bronze to gold level tables. Along the way, we used recommended best practices for maintaining our single source of truth and complying with security standards. Okay, well, thank you very much for your time. Please ask any questions in the Meeting Play forum in the remaining time, and we'll be sure to answer them. Thanks a lot. Have a great summit.